basically a very common laser, which is helium neon laser. And as the name suggests, HE stands for the helium, NE for the neon. It's a helium neon laser. Some of the basic features of helium neon laser is like it's a 4-level gas laser. It's a gas laser is natural because the active medium is we are using as a gas. This is helium or neon gas. It's a 4-level laser. That means we had already discussed about the 3-level and 4-level lasers for the lasing action. In 4-level, we have the advantage over the 3-level is that achieving the population inversion is quite easy in a 4-level system as compared to the 3-level system. So and the second one is the operational wavelength of this helium neon laser is around 632.9.8 nanometer, that which is 6328 angstrom. And we know that this comes in the region of the red color of visible spectrum. So naturally the lasing output is going to be of red color. As you can see here, this is the region where the laser transition comes of 632.8 nanometer. It's a continuous laser. That means once the output comes out from the system, it's continuous. It's not going to stop till the system is on. The fourth one is its output power can be tuned between 1 megawatt to 100 megawatt, and its gain medium, or say active medium, is a glass tube filled with the helium neon gas at the ratio of 10:1. At very low pressure it is about around 1 torr. So this is a very common helium neon gas laser in which achieving a population inversion is very different. So let's discuss it on a mix because you can see here a mixture of about 10 parts of the helium, 10 parts of the helium, and 1 part of the neon is there at low pressure of around 1 torr is placed in a glass tube. You concentrate here is placed in the glass tube. This is our glass tube, and has a parallel mirror at both the ends. One is a fully silvered mirror and the other is partially silvered mirror, through which we are going to get our beam. And the spacing between these two mirrors, say spacing between these two mirrors, has to be an integral number of half wavelength of the laser light. That means that before constructing the helium neon laser, we know that what kind of transition we are going to get for the lasing action, so that we keep the distance between the mirror between which our photon are going to get uh, travel. It has to be an integral multiple of half wavelength of the laser light, and an electrical discharge is supplied to the system of the active medium through a super high frequency alternating current through these you can say these discharge electrodes. So this is very simple construction for a laser, very common gas laser. What happens that when we supply the energy to the system active medium through the discharge tube, we know that at the thermal equilibrium most of the atoms, okay, let's say atoms of this is the helium neon gas, and this is the part of the neon. So say this most of the atoms are there in the ground state at thermal equilibrium, and see, and let's see, this is for neon atoms. So when we supply the energy through the discharge tube, so the atoms which are in the ground state of the helium and the neon got excited and absorb energy and got excited to uh, level which is above the ground state. Here in this case, we have uh, mm, you can see here. So after absorbing the energy, these atoms which are in the ground state, they got excited to um, the higher energy state. These states basically are this one, 20.61 electron volt and 20.66 electron volt. So these states are actually the metastable state for the helium atom. This is 20.61 electron volt and 20.66 electron volt. This is the metastable state in the neon atom. Okay, neon gas, or say neon gas, and in the helium gas. So directly from the ground state, achieving an energy, this atom goes to their metastable state in the helium system and in the neon system. Further, what happened that because uh, there are 10 parts of the helium atom and one part of the neon atom is there. So in such system, you can see that the metastable state of the helium atom, which is 20.6 electron volt, and 20.66 electron volt of this helium atom are very close to each other, which is almost only 0.05 electron volt difference is there. So these two metastable state are very nearly same at the same position there, that is 20.61 and this is 20.66 electron volt. Okay, they are very close to each other of helium atom and neon atom. So what happens, some of the excited atoms uh, of helium excited atom transfer their energy to the ground state neon atoms in collision. Okay, so some of these excited atoms transfer their energy to the atoms which are in the ground state of helium atoms. Okay, with 0.05 electron volt of additional energy being provided by the kinetic energy of the atoms, because we need 0.05 electron volt more energy than this atom to go to this state, to come to this state. So when the atoms which are excited atoms of helium, they collide with the ground state of atoms of the neon atom, they supply their energy and they move to the metastable state of the neon atom. And the purpose of the helium atom is thus to help achieve population inversion in the neon atom. So what happens when we are supplying energy? By the supply of the energy, the atoms of the neon are going to this metastable state, and another way also, the helium atom, which are helium atoms which are colliding with the ground state of the neon atom, they are also providing energy to the atoms in the ground state of the neon, and the more and more atoms are going to the neon states. That's why we are going to have a population inversion uh, in the neon system, that the more and more atoms are there in the metastable state of the neon atom as compared to the ground state of the neon atom. So the population inversion is achieved with the help of the helium atoms. So the purpose of the helium atom is to help achieve the population inversion in the neon atom. So the laser transition in neon atom is from the metastable state, which is 20.66, okay, electron volt, to an excited state of 18.7 electron volt. So this is 18.7 electron volt. This is what this intermediate state of 18.7 electron volt with the emission of 632.8 nanometer photon. Then another photon is spontaneously emitted in transition to a lower metastable state, and which is this from this state to this state there is a spontaneous emission, transition to uh, lower state, metastable state, and this transition yields only incoherent light. Okay, so the the photon which are coming in this transition from this to this, which is a spontaneous, these photons are basically incoherent, they are not coherent. So the remaining excitation energy is lost in collision with the tube walls. Okay, so when the atoms are coming from this state to the ground state are basically radiation-less transition. That means the atoms are colliding with the walls of the cavity, and during that collision, they lose their energy and come to the ground state. So, because the electron impact that excites the helium and neon atom occur all the time, unlike the pulse excitation from this. Okay, forget about this. Uh, I'll stop here. That now let us understand again the total process of the lasing action. So what happens? We supply the energy to the system, which is a mixture of helium and neon gas. Helium neon is a 10 part, and helium is a 10 part, and neon is 1 part. So when we supply atom to the ground state of helium and neon system, so the atoms which are in ground state of helium neon goes to excited state, which is basically the metastable state of 20.61 electron volt and 20.66 electron volt, and addition atoms are provided in the metastable state of uh, of the metastable state of the neon, while when the helium atom which are in the excited state collide with the atoms which are in the ground state of neon, they further supply the atoms to the metastable state of the neon system, and through this we achieve a population inversion. That is, more and more number of neon atom is there in the metastable state as compared to the this level, which is another metastable state, and as compared to this or this or this, there are more number of atoms in this metastable state, so population inversion is achieved. And then we have a lasing transition by stimulated emission from this level to 18 point from this level to another level, which is 18.76 of electron volt, and this energy is 632.8 nanometer. This is where we get a photon, a stimulated photon, and these photons travel in this medium back and forth here and here. So this is the cavity, and the photon travel back and forth here in this cavity, and because the distance between these cavities is an integral multiple of half of the wavelength in order to make the standing waves. So more and more photons are being trapped in this cavity, and they are being enhanced, their energy density is being enhanced, and when the energy density is so and the power is so high that from this partially silvered mirror, the beam you see is the laser beam comes out from the system. Okay, and the atoms which comes here in the at this state 18.7 electron volt, they spontaneously through a spontaneous emission comes down to this level. So the photon which are coming during this transition from here to here are basically incoherent. We don't have to consider these incoherent photons, and then from this level to the ground state, the atoms comes by losing their energy with the collision of the walls of the cavity. This is how the total helium neon laser action takes place. This is the laser whose narrowed beam is used in the supermarket to read the barcodes, used for a holographic purpose, producing the 3D images of the object, and many industrial and scientific uses, and are often used in the laboratory for the demonstration of the optics. So normally when you see in the physics lab, this helium neon laser is used for various type of experiment. So this is a very common laser, and I think now you have a flavor of how it works, what is construction, basic features of this helium neon laser, which is a solid state laser, and it is a three-level laser. uh, it is a three-level laser and it's a solid state laser. So the active medium is a solid state device, and it is three-level laser in which we have a ground state, and we have excited state of energy of 2.25 electron volt and a metastable state of 1.79 electron volt, and then we have a ground state. So naturally the population inversion has to achieve between this state and this state, ground state. Okay, so this is some ordinary state whose lifetime is going to be around 10 to the power minus 8 second, 10 to the power minus 8 second, sorry, 10 to the power minus 8 seconds, and its lifetime is 10 to the power is about uh, 0.003 seconds. Okay, so it's a three-level solid state laser, and the operational wavelength is of 694.3 nanometer, that is 6943 angstrom, which is again a red color laser, and it is a pulse laser. That means it's not continuous. So because we are using a flash tube for the optical pumping, so it's a pulse type. For a certain time the energy is supplied to the system, and for that time, for the fraction of a second, we get the output of the laser, and then it stops, and then again for after some certain time interval we get a laser beam, and then it stops. So it's a kind of pulse laser. The gain or active medium of this ruby laser is basically a synthetic ruby crystal. You can see there's a ruby crystal here. This to the whole system is a synthetic ruby crystal, which is basically the aluminum oxide, and in which the aluminum Al3 plus ion is replaced by the chromium ion, 0.05% in weight. And basically the chromium ion Cr3 plus is responsible for the red color of the ruby. So the construction is very simple. We have the first successful laser, the ruby laser, is based on the three energy levels, in which the chromium ion is responsible for the lasing action. So a ruby crystal, which is aluminum oxide Al2O3, in which some of the aluminum Al3 plus ions are replaced by the chromium ion Cr3 plus ion, which are responsible for the red color. So a chromium ion has a metastable state of uh, 1.79 electron volt, whose lifetime is about 0.010 to the minus 3 second. So in the ruby laser, we use a xenon lamp. You can see this is a xenon lamp, which is around this ruby crystal uh, is there, which excites the chromium ions which are present inside this ruby crystal. Okay, so uh, what happens when this xenon lamp supplies certain energy for certain time, the chromium ions which are in the ground state, which are present in the ground state of the chromium uh, system, get some energy and move to the higher energy, from which they fall. From here they move to, you can see they move to the higher energy level here, and from here basically um, they spontaneously decay, or from where they fall to the metastable uh, level by from here, from this system, from here they fall to the metal stable state by losing energy to other ions in the crystal. And since the atoms which are here and they are coming from here, this state to this state to this is metastable state, by losing their energy with the collision with the other ions which are present in the crystal, therefore this is a radiationless transition. So the atoms, by gaining energy, the ions, the chromium ion, by giving energy from ground state to this higher energy state, which is 2.25 electron volt, and then from here, from this level, they come to this level by collision with the other signs which are present in this active system. Therefore this is a radiationless transition. And from here, and when the atoms are present here in the metastable state, we achieve the population inversion between the metastable state and the ground state. And once we achieve the population inversion, we get through stimulated emission, we get more and more photons through stimulated emission in the system, and of the order of 694.3 nanometer, or 6943 angstrom of photon. Okay, so these photons from the stimulated decay of some chromium ions are reflected back and forth between the two ends, this end and this end of the mirror ends of the ruby rod. So the photons which are coming from this stimulated decay of some chromium ions are reflected back and forth between the mirror ends of the ruby rod, and and they further stimulating other excited chromium ions to radiate more and more photons. And after a few microseconds, the result is there is a large pulse of monochromatic coherent red light from the partially transparent end, you can see here, is coming as a consequence of the lasing uh, action. So this is a simple working of the ruby laser, in which we supply certain energy from the flash lamp, and the chromium ions which are present in the ruby rod are getting excited to a system of 2.25 electron volt, and from there they collide different ions which are present in the ruby red ruby crystal. Through radiationless transition they come to the metastable state, and the moment we achieve the population inversion, we get more and more photons through stimulated emission, and all these photons are reflected back and forth between the mirror ends of the ruby rod, and during that travel they stimulate more excited chromium ions to radiate further and further, and after a few microseconds we get a large, intense, coherent and monochromatic pulse in terms of the lasing beam. Okay, so it's fine for the ruby laser. Thank you.